So let's talk about first order reaction and derivation. So we have so far expressed the rate of a reaction as a function of the reactant concentrations. So that is, we have only discussed the differential rate law. It is also useful to be able to express the reactant concentration as a function of time. That is why we are discussing the integrated rate law. So let's proceed by looking at the equation above. So we have B gives the products there. So we can write the rate expression for the equation above as rate equals to negative the B over the T to give K B N. So in case N is the order of the reaction, and when N equals to 1, it is first order reaction. It is second order when N is 2. So N can be 3, and N can be 0 as well. That is 0 order. So N can also be a fraction, and that's fractional order. So N can be a positive, can also be a negative integer. So now let's talk about the first order reaction. So the equation for the first order reaction can be expressed as ln B at time t equals to negative kt plus ln B naught. So this is the initial concentration. So this is the final concentration. So this is a rate constant. It can also be proportionality constant. So this is time in any units of time. So the above first order reaction equation can also be written as log B minus X equals to minus KT over 2.303. It is important to remember that when you are using log, you have 2.303 here, but in the case of natural logarithm, in the case of ln, they are not using 2.303. So we have plus log B. So to derive the first order reaction, so derivation, let's talk about the derivation now. So this is the equation. We have B to give the product. So at time t equals to 0, at time, this is time, equals to 0, we have that the concentration of B is B, and the concentration of the product 0 mole per dmk. So at time equals to t, we have this to be B minus X, and we have this to be X mole per dmk. So we can therefore write the rate to be the rate of the reaction in terms of the concentration of the product can be the X over the T equals to what? Equals to K in the bracket B minus X. So because it's first order reaction, we have 1 here. So we can simply write it as the X over the T equals to K B minus X. So n to the raised to the power 1 is staying as itself. So we have this. So the next step is to multiply through by the t and divide both sides by b minus x. So we have the x over the t, and we have the t over b minus x equals to we have k into bracket b minus x, and we have the t over b minus x. So we expect this to cancel out this. We expect this to cancel out this. Therefore, we have the x over b minus x equals to k dt. So let's take the natural logarithm of both sides. So when x equals to 0, when x equals to x, and natural log when we have time to be 0 and when time is t. So let u equals to b minus x, and therefore we have that the u over the x equals to 0 minus 1. So we can say that the x equals to what? Negative du So now let's have that x equals to 0, x equals to x, and therefore we have this x 1 over u du. So we have the negative here. Negative here is here. So we also have that integral of t k dt. So we can simply say that negative ln u x 0 equals to k t naught. So we have that. Let's put u equals to x back into this equation. We have negative ln b minus x at the point of where x and 0. So we have kt ln t and 0. So when x is x, we have this equation. When x is 0, we have this to be ln b. So we can say that ln b minus x, minus ln b, so equals to, so when t is 0, everything a becomes 0. So we have kt minus k0. So we can say that negative ln b minus x over b equals to kt. So we can therefore say that ln b minus x over b equals to negative kt. So therefore we have that ln b minus x equals to minus kt plus ln b. So we can put this in terms of log. We have log b minus x equals to minus kt over 2.003 plus log b. So this is the final. So this is the initial. This is the initial concentration, rather initial. This is the final concentration, and this is the rate constant, and this is the time. So there are several important notes about the equation of the first order reaction. So important notes. Let's put it in. Important notes. So the first note is that the equation is of the form y equals to mx plus c. So we can therefore say that this is the y, this is the x, and all of this is x. This is m, and this is c. So we have that y equals to what? Log b minus x, or ln bt. So our n, which is the slope or gradient, equals to minus k over 2.003. So we have that our x is the time in seconds or minutes or any other unit of time. So our intercept is the log b. So this is intercept. So if you plot this, so we have that this is the y-axis, so this is the x-axis. So this y-axis is the same thing as log b minus x, and this x-axis is the same thing as our x, so which is t. So same thing as time. So because the value of our slope is negative, so we can say that the intercept equals to minus k over 2.302. So therefore, a plot of this against the time we always give a straight line graph. So it is always a straight line graph for a first order reaction. So first order reaction equals to this straight line graph. So now let's talk about the half-life of first order reaction. So if you say that the equation for a first order reaction is log b minus x equals to minus kt plus log b. So the first order and half-life of the reaction, half-life T1 over 2. So half-life of a reaction is the time required for the concentration of the reactant to decrease by half. So this is the reactant. So the concentration, initial concentration of the reactant decreased by half to its initial value. So at half-life, B becomes B over 2, or simply replace B minus X, or simply replace B minus X with B over 2. So therefore we have that at half-life, log B over 2 equals to negative this plus log B. So we have that we have that kt equals to log B over 1 divided by B over 2, and we have it to be log B times 2 over B. So this cancels this. So we have that kt equals to log 2. Therefore, we have that, we have to put that this is half-life. So this is half-life. So this also is half-life. So 1 over 2 equals to 0.693 over K. So this is the half-life of a first order reaction. So the units of a first order reaction, units of rate constant for first order reaction, R equals to K into bracket B1. So the rate of a reaction is molar per second, and the rate constant is unknown. So the concentration is this. So we have that K equals to X over 1 over N. So this cancels out. So the unit of the rate constant for a first order reaction is per seconds, or per unit of time. So here is a question. The first order reaction is 45% complete after 400 seconds. So how long will it take for the reaction to be 90% complete? So the kinetics for a first order reaction is log B minus X equals to minus kt over 2.303 plus log B. So this is the final, and this is the initial concentration, and this is the final concentration. So we have that the initial concentration percentage, the maximum percentage we can have is 100. So the initial concentration is 100%. So that's one. So the first order reaction is 45% complete. That means our X is 45%, and that's simply 0.45. So b minus x equals to what? 1 minus 0.45, and that's 0.55. So we can see, therefore, we input these values into the equation. We have log 0.55 equals to minus k times 400 seconds times 400 plus log 1. So therefore we have that 400k equals to, this is 1 log 1 over 0.55. So we have k to be equals to 1.495 times 10 raised to the power minus 3 s minus 1. Remember that the unit of rate constant for a first order reaction is per time. So we have this. So therefore, the second part of the question says, how long will it take for the reaction to be 90% complete? So for the reaction to be 90% complete, it means we have let's put a demarcation here. So it means 90% complete is the same thing as x equals to 90%, which is 0.90. So we have b to be 100%, which is the same thing as 1. We have b minus x to be 1 minus 0.90, and that's 0.10. So therefore we have that log 0.10 equals to 1.495 times 10 raised to the power minus 3 s minus 1 times time plus log 1. So we therefore have that t equals to log 1 over 0.10 times 1 over 1.495 times 10 raised to the power minus 3. So we have that time to be equals to 1541 seconds. So you can try it out and ensure that you get the same answer. So looking at the question above, the decomposition of the reactant follows the first order kinetic and its half-life is 40 seconds. So what fraction of the reactant would have decomposed after 60 seconds? So first order kinetics, we have log b minus x equals to minus kt over 2.303 plus log b. So fraction decomposed is the same thing as x over b, that is fraction lost over total fraction. So we therefore have that log b minus x equals to minus k times 40 over 2.303 plus log b. So let's look at the question 2 above. So the decomposition of the reactant follows the first order kinetics and its half-life is 40 seconds. So what fraction of the reactant would have decomposed after 60 seconds? So let's have the solution here. So the half-life for a first order reaction is this, is represented as 0.693 over K. So therefore we can say that K equals to 0.693 over 40 seconds. And so we have K to be equals to 0.0173 S minus 1. So the equation for first order kinetics is log B minus X equals to minus KT plus log B over 2.303. So we have this to be the initial concentration. So this is the final concentration. So from the question, the decomposition of the reactant follows first order kinetics, and its half-life is this. So what fraction of the reactant would have decomposed after 60 seconds? So after 60 seconds, we expect that the fraction to have decomposed to be represented by this fraction decomposed equals to amount decomposed over the total amount. So, and it's also the same thing as X over B. So we can therefore express the equation above as log B minus X equals to negative 0.0173 times 60 seconds over 2.303 plus log B. So therefore we can say that, let's map this place out. So therefore we can say that log B minus X equals to 0.451. So we have that. So log B over B minus X equals to 0.451. So taking the antilog, we have that B over B minus X equals to 10 raised to the power 0.451. So we have that this to be equals to 2.825. So we therefore have that B minus X over B equals to 1 over 2.825, and that's equals to 0.35. So we can therefore say that B minus X equals to 0.35B. So we have that. So therefore B minus 0.35B equals to X. So this thing is the same thing as